Okay, hi. This is my video number 6. So in this video I'll talk on some theorem on orthogonality of the eigenfunction, and there are the real of the eigenvalue for the symmetric kernel. Okay, so let us see the first theorem. The eigenfunction of the symmetric kernel theorem. So the eigenfunction of the symmetric kernel of the homogeneous Freedom integral equation with respect to two eigenvalues are orthogonal. Of the, I just write in short form, homogeneous Freedom integral equation corresponding to two distinct eigenvalues corresponding to two eigenvalues are orthogonal. Okay, first thing is you know what eigenvalue is, you know what eigenfunction, and you know what is eigenvalue. Eigenfunction is the solution, basically is a non-trivial solution corresponding to the eigenvalues for the homogeneous Freedom integral equation. Now regarding to this theorem, symmetric kernel means the kernel that can be written as kxt is equal to ktx. Okay, and the orthogonal means if we have eigenfunctions, let's say we have two eigenfunctions, phi1, phi2, then the orthogonal means we integrate with respect to x of, let's say, phi naught x, phi2x, sorry, phi1x dx. This must be 0. Okay, where phi naught and phi1 is the eigenfunction with respect to eigenvalues lambda 1, lambda naught, and lambda 1. So what we want to show, if this is the condition, I mean the eigenfunction for the symmetric kernel, then the eigenvalues, then the eigenfunction is are orthogonal. So we need to show this. Now we consider the Freedom integral equation of the homogeneous Freedom integral equation of the second kind, which is ux is equal to lambda integrate ab k xt ut dt. Okay, we're going to prove this, and we let phi naught x and phi1 x are the eigenfunction corresponding to eigenvalues lambda naught and lambda 1. So therefore we can write phi naught x is lambda naught ab k xt phi naught t dt, and phi1 x as lambda 1 ab kxt phi 1t dt. We can do this because the eigenfunction, basically the solution of our homogeneous Freedom integral equation corresponding to the eigenvalues. So which means it must satisfy the homogeneous Freedom integral equation. So let's give a name. Let's say this as equation 1. I'll go with this as equation 2. Okay. Now, in order to prove this, we multiply 1 with phi 1 x, and then we integrate from a to b with respect to x. Okay, so what we have now is that if equation 1 we multiply by phi 1 and integrate, so it means we have to integrate a to b, phi naught x, phi 1 x dx, this is equal to, so lambda naught integrate a to b, you can put it phi x here, yeah? So this is phi 1 x, and integrate a to b kxt phi naught t dt. Now, if we change the order of integration on the right hand side here, yeah, change the order of integration, that will give us, let me write in full. So on the left hand side we have integrate a to b phi naught x, phi 1 x dx. On the right hand side, I change the order of integration, so we have lambda naught integrate a to b, this is phi naught t integrate a to b k and xt phi 1 x dx dt. Okay, and since k is matrix, I have mentioned here, and in fact we have defined earlier, when k is matrix means k can be written as kxt as a k dx. So therefore I can write this equation, since k is matrix, we have integrate a to b phi 1, okay, or phi naught x or phi 1 x, phi naught x, phi 1 x dx. This is equal to lambda naught a to b phi naught t integrate a to b ktx tx phi 1 x dx dt. And equation number 2, from equation number 2 here, I put number 1 and number 2 here. Yeah, from equation number 2, we can change the variable. Yeah, we can change the variable. This is the integral variable, so should have no problem with that. So from 2, I can write phi 1 t is equal to lambda 1 integrate ab k tx phi 1 x dx. Okay, and then which is I can write this as a integrate a to b k tx phi 1 x dx. This is equal to phi 1 t over lambda 1. So I can substitute this value here into here. Okay, let's call this number 3, equation number 3. Okay, and then we substitute this value into that, substitute into 3, we have integrate a to b phi naught x phi 1 x dx. This is equal to lambda naught integrate a to b phi naught t, and we have that is phi 1 t over lambda 1. Okay, that's dt. Okay, and then of course I can take out the lambda 1, so we have lambda naught over lambda 1 integrate a to b phi naught t phi 1 t dt. And then I can multiply to the other side lambda 1, so we have okay, from here we can multiply lambda 1 to the left side, so what we have is lambda 1 integrate a to b phi naught x phi 1 x dx. This is lambda naught integrate a to b phi naught t phi 1 t dt. Okay, and of course since this is the integer variable, I can always change that. So I can write this as a lambda naught a to b phi naught x phi 1 x dx. Okay, then you can bring it to the other side, that give us lambda 1 minus lambda naught integrate a to b phi naught x phi 1 x dx, that equal to 0. And since this is the eigenvalues, two different eigenvalues, so which means we have, since lambda 1 cannot equal to lambda naught, so which means lambda 1 minus lambda naught is different than 0. So to have that 0, so we must have integrate a to b phi naught x phi 1 x dx, this equal to 0. So this shows that the eigenvalues with the corresponding to eigenfunction corresponding to eigenvalues lambda 1 lambda naughts for the homogeneous Freedom integral equation is orthogonal. And we have another theorem. That eigenvalues of the symmetric kernel of a homogeneous Freedom integral equation are real. Yeah, so eigenvalues of the symmetric kernel of homogeneous Freedom integral equation are real. Now, how to prove this? The homogeneous Freedom integral equation. So we consider the homogeneous Freedom integral equation. Consider ux x lambda a b xt ut dt. Okay, and we suppose that this equation here, the homogeneous Freedom integral equation, has a complex eigenvalue. So let's lambda naught equal to alpha plus I beta, because it has the complex eigenvalue. And we also let the corresponding eigenfunction phi naught x is equal to u plus iv, because if the eigenvalue is complex, then we should have the eigenfunction complex as well. And therefore, if lambda naught is the eigenvalue for that equation, means the conjugate of those is also the corresponding eigenvalue. So therefore we can have lambda naught conjugate of those is alpha minus beta, and as well as the eigenfunction conjugate of those minus iv. Okay, now since phi and phi naught conjugate are the eigenfunction corresponding to the lambda naught and lambda naught bar, so it must satisfy the homogeneous Freedom integral equation. Thus we have phi naught x is equal to lambda naught integrate ab kxt phi naught t dt. All right, and also we have phi naught x bar. This is equal to lambda naught bar integrate a to b k xt phi naught t bar dt. So let's call this equation number 1, and I call this equation number 2. Now I can multiply equation number 1. Okay, from equation number 1, we multiply 1 by conjugate of phi naught, and we integrate over x from a to b. Okay, so what we have, so integrate from a to b, that we multiply by phi naught, so we have phi naught x bar dx on the left side. On the right side we have lambda naught integrate a to b phi naught x, okay, and integrate a to b kxt phi naught t dt dx, right? And then if we change the order of integration on the right hand side, so what we have on the right hand side, we have lambda naught integrate a to b. I can change that. We have phi naught t, and this is integrate a to b, and our kernel is symmetric, so I can write that as a tx, and this one is phi naught x bar dx dt. Okay, and then from that equation, from 2, we can write from 2 we have phi naught phi naught x. So we have lambda naught. This is tx, and this is phi naught. So I can write this, just change the variable there. So I can have phi naught t is equal to lambda naught integrate a to b k tx phi naught x dx. And therefore we have from there from this part here we have integrate a to b k tx phi naught x bar dx. This is equal to phi naught x over lambda naught bar. And then we substitute into that equation. Let's call this number 3. Okay, let's call this equation number 3. Okay, so we substitute this into 3. Substitute that into 3. So what we have, substitute into 3. So what we have, integrate a to b phi naught x bar dx. This is equal to lambda naught integrate a to b phi naught x, and then we have that one is phi naught x bar over lambda naught dx. Okay, and then rearrange this. Okay, I can multiply this lambda naught to the left side. So we have lambda naught bar integrate a to b phi naught x bar dx. That's equal to, we have lambda naught integrate a to b phi naught x bar dx. Alright, and we can bring that to the other side. So we have, you can write this lambda naught minus lambda naught bar integrate a to b phi naught x bar dx, that equal to 0. But we have assumed that our phi naught, yeah, we have assumed that our phi naught is equal to where is it, alpha plus, yeah, lambda alpha plus I beta, and our phi is u plus iv. So we have here lambda naught is alpha plus I beta. So what we have, we need to substitute into that. So lambda naught minus lambda naught bar, that give you alpha plus I beta minus alpha minus I beta, that give you 2I beta. Okay, and also for phi, we have here our phi is given as u plus iv, this one here. So our phi naught is u plus iv. So if you substitute that, multiply those things, so phi naught x and phi naught bar, this give you u plus iv times u minus iv. Okay, that give you u squared plus v squared. So and basically this cannot be 0 because lambda is our eigenvalue, so this is not 0. Alright, So if you substitute this value here, that and that, into this equation here, so what we have is that 2I beta integrate a to b u squared plus v squared dx, that equal to 0. Okay, and since this part cannot be 0, that part cannot be 0 because of this, and phi is the eigenvalues, so what we have is beta is just 0. Yeah, so therefore we have beta is 0. So which means in this case our eigenvalue that's, we assume earlier that in this form alpha plus I beta. Now beta is 0, so what we have is only alpha. So therefore the eigenvalues is only real number. Okay, so that's the proof of that theorem. Now I'll give you example, 1 or 2 example. Let's see how's things going on. This thing is not correct. How can I make it more strict? Okay, all right, that's better. Now example, we want to find the eigenvalue and the corresponding eigenfunction for the homogeneous Freedom integral equation. Ux is equal to lambda integrate 0 to 1 sine pi x cos pi t ut dt. Okay, you can put bracket there, and obviously you can recognize this. This is the separable kernel, so I can take out this sine pi x outside the integral sign, so I can write this basically. So ux is equal to lambda sine pi x integrate from 0 to 1 cos pi t ut dt. Now if we define this part here, okay, define that as a c integrate 0 to 1 cos pi t ut dt, then what we have, that equation we reduce to, so you have ux is equal to lambda sine, I can put c there, so lambda c, I can put it lambda c sine pi x. And of course I can change those variable. Yeah, I can change those variable. The purpose is that we want to evaluate c, and c here you have a function of t, ut, so I can change that, so ut, so therefore we have ut is equal to lambda c sine pi t. Okay, so then if you substitute into equation, definition of c, so we have that c, so therefore our c is equal to, so we have this is ut, so lambda c, I can take out the lambda c, so that gives you lambda c integrate 0 to 1 cos pi t sine pi t dt. Okay, then of course here you can evaluate those things. Okay, if you evaluate this, you can evaluate this part here, not a big deal. You can use a integration by parts, and so on. So the whole thing is now, and then you can factor out c. Of course, then this part cannot be 0. Then what you have is c equal to 0. Yeah, you can proceed further those things. And then when c equal to 0, if you substitute into our solution here, we can substitute our solution here. So therefore our ux is equal to 0. So which means we only have trivial solution. So therefore the given equation has no eigenvalues and no eigenfunction. So therefore the given equation, the homogeneous Fredholm integral equation has no eigenvalues and no eigenfunction, corresponding eigenfunction. Okay, so that's the first example. Now let me give you another example. So this example with the eigenvalue. Okay, we can find the eigenvalue. So again, we want to find the eigenvalue and eigenfunction for this integral. So ux, I think you can write here, find the eigenvalues and the corresponding eigenfunction. Corresponding eigenfunction for, so ux is equal to lambda integrate 0 to pi cos squared x cos 2t plus cos 3x cos 3t ut dt. Okay, so you have ux equal to lambda 0 to pi cos squared x cos 2t plus cos 3x cos cube t ut dt. So that's the equation given. And from the given equation here, I can write this thing. Of course, we can split those. So that gives you ux is equal to, for this, we can take out the function that involves x. So we have lambda cos squared x integrate 0 to pi. Then we have cos 2t ut dt. And for this, plus lambda cos 3x integrate 0 to pi cos 3t ut dt. Okay, just expand the given equation. Now we define that part, the integral that involves unknown function u. We define that part. Let's say this is as a c1. Let's say this is as a c2. So let's write it down. Okay, define c1 equal to integrate 0 to pi cos 2 pi ut dt, and c2 integrate 0 to pi cos cube t ut dt. Then therefore we have our u becomes ux is lambda c1 cos squared x plus lambda, so we have that one, we have this lambda c2 cos 3x. Okay, now we need to find C1, C2. So in order to find C1, C2, we need to identify what U is. Okay, and from here we have UT, and here we have UX. I can change the variable there. I change the variable, put the x equal to t. So what we have, this is just UT equal to lambda C1 cos squared t plus lambda C2 cos 3t, and then I can substitute into that. Okay. So if you substitute there, what we have, therefore C1, I use that one first, C1 is equal to integrate 0 to pi cos 2 something 2t here, sorry, this is 2t, cos 2t here. So cos 2t, and the ut is given here. You can write it down, lambda C1 cos squared t plus lambda C2 cos 3t dt. Okay, and then you can factor out c, put that the other side. So what we have is C1, you have 1 minus, you have lambda here, lambda. Okay, C1 we have already taken it out. So what left is 0 to pi, and this part here you have cos squared, cos 2t, alright, and then cos squared t dt, and we have another one here, minus lambda C2 integrate 0 to 2 pi cos 2t cos 3t, right? Okay, 3t dt, that equal to 0. Okay, we just substitute the value, the u into C1, then give us this. Okay, and then from here I can consider this as to make my writing easier. Right? I can call this as I1. I can call this as I2. All right, and then you can write those equation becomes C1 1 minus lambda I1 minus lambda C2 I2 that equal to 0. Of course, I1 and I2 you can evaluate this. Yeah, if you evaluate this, it will give you a pi over 4. Okay, and if you evaluate this one, that give you let me check my notes, that's 0. Okay, now in order to evaluate this, you need to use the appropriate identity. In my case, I use half 1 plus cos 2t, and then for this one you can use equal to cos half cos 5t plus cos t. Yeah, this is equal to that. So evaluate this, that give you 0. Evaluate this, you give you pi over 4. And then therefore, if you use this value into our C, where is our C? Here. Okay, use this value I1 and I2 here. So we have C1, where is C1? So we have 1 minus this is pi lambda over 4, all right, C1 minus, here we have 0 times C2, 0. So basically we have from there, you have C1 cannot be 0, C2 not necessarily 0, because if it's 0, then if C1, C2 0, so we have the trivial solution. So C1, C2 cannot be 0, so therefore this part should be 0, then that gives you lambda is equal to 4 over pi, alright, I think 4 over pi, so 4 over pi, 4 over pi. Okay. Now you can do the same. Now we apply C2. Okay, you apply C2 with U that we obtained earlier here. That's with that U and just UT with that. Just proceed the same. You will have let me write this thing, substitute UT into C2 into C2. So you have lambda C1 I3 plus C2 lambda I4 minus 1 equal to 0. Yeah, with I3 is equal to 0 to pi cos 5t dt. If you evaluate that, give you 0. And your I4 is integrate 0 to pi cos cube t cos 3t dt, and this give you pi over 8. Okay, now use this value here, I3 and I4 into that equation. So what we have is that 0 C1 plus we have a lambda pi over 8 minus 1 C2 that give you 0. Okay, so from here we have lambda equal to 8 over pi. So we have two value of lambda here. Let's call this lambda 1 pi over 4. Let's call this lambda 2 pi over 8. Yeah, and if you find the this equation here and this equation here, you can check the determinant of those not 0. You can find, and then as well you can find the lambda 1 and lambda 2 that give you 4 over 8 and 8 over 4 over pi and 8 over pi. So with that, so the corresponding eigen function, so for lambda, let's say this is lambda 1 equal to 4 over pi. So we want to find the eigen function. We substitute into the appropriate u. So we have ux is equal to lambda c1 cos squared x. This gives you 4 over pi c1 cos squared x. Yeah, for this lambda equal to pi over 4 over pi, this will give you basic C2 is equal to 0. Just substitute into the equation that I mentioned earlier. Okay, then of course this is just a constant. You can choose any value there if you want, or you can leave it just like that. And for lambda 2 h/pi, you can find this C1 equal to 0. Then therefore your solution, you get the solution or eigen function as h/pi C2 cos 3x. So therefore we have phi 1, which is correspond to lambda 1. The solution is, you can take that as pi over 4/5 C1 cos squared x, and phi 2x as h/pi C2 cos 3x. Okay, and again, as I mentioned to you, this is a constant. You can choose this equal to 1. You can choose this equal to 1. So that your eigen function just cos squared x and phi 2 equal to cos 3x if you choose that equal to 1. So with that example, so I have explained in this video the two quite important theorem, that the eigenfunction for the homogeneous Freedom integral equation with the symmetric kernel, they are what we call orthogonal, and the other one is the eigenfunction is a real value. And I give two examples of how to solve the Freedom integral equation, homogeneous Freedom integral equation, with the separable kernel. In the previous video also I have give example on almost this, for the separable kernel. So with that, thank you. We meet again in the next video. Bye bye.